Assalamualaikum and hi, my name is Nur Aina Zafira binti Zainuddin. So in this video, my groupmate and I gonna present to you our project for applied thermodynamics. So first of all, let me introduce my groupmate. First we have Muhammad Kamal Haikal bin Abdul Kamaluddin, and then we have Lim Chuan Yi, and then we have Irfan, and lastly we have Hariharan Raj. So first for the introductions. So in this project, we have three designs. First we have a gas power plant, and then we have a vapor power plant, and then we have a combinations of vapor and gas power plant. So in this project, we have to know the PV and TS diagram for each design, and then we have to know the efficiency of each design, and then we have to know the coal required for each design, and lastly we have to know the advantage and disadvantage of each design. So first we go to TS and PV diagram for each design. So first we have the gas power plant. So for the gas power plant, we refer the Brayton cycles. Why? Because the Brayton cycle is the ideal cycle for gas turbine engines. So we have the given data, which is the inlet turbine temperature is 1000 Kelvin, and then we have the compressor isentropic efficiency, which is 95%, and then we have the turbine isentropic efficiency, which is 85%. And then we assume some data. First we have the compressor inlet temperature, which is 300 Kelvin, and then we assume that the pressure ratio is 12. So in this slide, we see the TS diagram for the gas power plant and the PV diagram for the gas power plant. So next, we have the vapor power plant. For the vapor power plant, we refer the Rankine cycle, which is the ideal cycle for the vapor power cycles. So the given data is 80% energy transferred to the steam, and then we assume that the turbine inlet conditions of 6 megapascal and 400 Celsius, and then we assume that the condenser pressure is 4 kilopascal, and then we assume that the efficiency of the electric generator is 100%. So in this slide, we see the TS diagram for the vapor power plant and the PV diagram for the vapor power plant. Lastly, we have the combinations of vapor gas power plant. So in this power plant, we assume that the exhaust gases leave the heat exchanger at 400 Kelvin. So the other data we got from the gas and then the vapor power plant, and then we assume that the exhaust gas leave the heat exchanger at 400 Kelvin. So this is the TS diagram and the PV diagram for the combined vapor gas power plant. So now I'm gonna pass to my friend Kamal.
Wabarakatuh. My name is Muhammad Kamal Haikal. So I would like to present about my part, which is the gas power plant. So this is our design for our gas power plant, which we start with compressor and go to combustion chamber, and lastly go to the turbine. So we can see there are 4 states in our plant, and we can proceed to calculation by using the assumption at temperature state 1, which is 300 Kelvin. We can get the enthalpy and pressure ratio by referring to the table, and then we can calculate the pressure ratio 2, which is the P2 over P1 times the pressure ratio 1, and then from the table we can calculate we can get the enthalpy at state 2S and temperature at state 2S. And then after that, we can calculate the enthalpy at state 2 by using the formula H1 plus H2S minus H1 over with isentropic efficiency of our compressor. And then we can proceed to state 3 by using the temperature 1160 Kelvin. And by referring to the table, we can get the enthalpy at state 3 and pressure ratio at state 3. We can calculate the pressure ratio at state 4 by using the same formula, but we change the input, which is the pressure at state 4 and pressure at state 3 times with pressure ratio at state 3. And we can get the H4S and T4S by referring to the table. After completing all this value, we can calculate the enthalpy at state 4 by using the formula H3 minus NT, which is the isentropic efficiency of our turbine, times with H3 minus H4S. And then, after we get all these values, we can calculate the Q in and Q out. And then we also can calculate the W net by using the value of our Q in and Q out. We can get 195.02 kilojoule per kilogram. After that, we can calculate the thermal efficiency for our gas power plant by using the formula W net over Q in, and then we can get 32.38%. So this is our thermal efficiency for the power plant. And then we can calculate the required coal to run our gas power plant by using the formula power output over with the heating value of coal and times with the thermal efficiency. So the calculation is 50,000 watt over with 29,300 kilojoule per kilogram times with 0.3238. And then we can get 5.27 kilogram coal per second used to run our gas power plant. So that's all from me. Thank you.
Okay, thank you. For the vapor power plants, in this slide there is two diagrams, which is working principle for the vapor power plant cycle and the TS diagram for the vapor power plant cycle. So to find out the thermal efficiency, first we know that P1 equals to 4K. The HF, SF, and the VF, we get the value in the thermodynamic table. So the HF value is 181.39 kJ per kg. For the SF is 0.4224 kJ per kg. VF, which is 0.001004 meter cube per kg. For the P2, the value is 6 megapascal. So for the W pump in, we use the formula V1 times P2 minus P1, and we found the value of 6.02 kJ per kg. And we know W pump in equals to H2 minus H1. So to find out H2, we use W pump in minus H1, and we found the value of 127.41 kJ per kg. In P3, the value is 6 megapascal. The H3 and S3, the value we will get from the thermodynamic table, which is 3,302.9 kJ per kg for the H3. For the S3 is 6.7219 kJ per kg K. In the P4, value of P4 is 4K pascal. The value of the S4 equal to S3. For the X4, we use the formula S4 minus SF divided by the SFG, which is 6.7219 minus 0.4224, and then divide by the 8.0510, and we will get the value of 0.7824. For the HU, which is HF times X4 HFG, which is 121.39 times 0.7824 times 2432.3, which is 2024.42 kJ per kg. So for the efficiency, which is 1 minus 2024.42 minus 121.39 divided by the 3,302.9 minus 127.41, and we'll get the 0.4007. For the efficiency overall, you use the formula efficiency combined times the efficiency and times for efficiency in general, which is 32.06%. So for the required coal to provide the heat source for the power plant for working, and we can use this formula. M equals to power output divided by the heating value of coal times efficiency overall, which is 50K divided by the 29.3K times 0.3206, and we will get a value of 5.32 kg per second. Thank you, and I will pass to my friends.
Assalamualaikum warahmatullahi wabarakatuh. My name is Ifram Azman, ID MA1908. Today I would like to present about combined vapor gas power plant. As you can see, combined vapor gas power plant is consist of gas cycle and steam cycle through heat exchange or boiler. Now moving to the equation. This gas cycle and steam cycle we already got it. Then to calculate the thermal efficiency, we have to use the ratio of mass flow rate using energy balance equation. E in equal to E out. Mass flow rate of gas time enthalpy at 0.5 plus mass flow rate of steam time enthalpy at 0.3 equal to mass flow rate of gas prime time enthalpy at 0.4 prime plus mass flow rate of steam time enthalpy at 0.2. Then you simplify, then we got the equation. Then we substitute all the variable. Then we got y equal to 0.0681. That is a relationship between a mass flow rate of steam and mass flow rate of gas. Next, for WNet, WNet gas plus mass ratio of mass flow rate time WNet steam. WNet gas, we substitute the variable from the value we got from before. 195.93 plus ratio of mass flow rate 0.0681 time WNet steam 1272.46. Then we got WNet overall 282.58 kilojoules, which mean that each of kilo of combustion gas produced, the combined plant will deliver 282.58 kilojoules of work. Then for thermal efficiency, equal to WNet divided by Q in. Substitute the formula that we got, then we got the thermal efficiency equal to 46.71%. Then for the coal, we use the formula M coal equal to power output over heating value time thermal efficiency. Then we got the coal equal to 3.65 kilogram coal per second. I think that's all for me. Thank you.
Greetings and a very good afternoon to our respected Applied Thermodynamics lecturer, Dr. Fazat Fariliantaba. My name is Hariharan Rajana Munedi and my metric number is MA17076. I'll be taking over this presentation to present and explain about the fourth question, which is to compare and tabulate the advantages and disadvantages of each design of the power plants. So